Arnak Dalalyan. Of the conditional mean and the conditional variance in high dimensions.
Thank you. Thank you also for inviting me here. So the work that I will present now is a joint work with Mohamed Eberi, Katia Mediani and Joseph Salmon from Paris. And the main aim of this work is to estimate in the same time the regression function and the uncertainty related to the regression function in the regression model under the context of sparsity in machine learning. So the focus will be very much different from the classical statistical point of view, where some smoothness assumptions are imposed, and under these assumptions the estimation of the conditional variance is carried out. Here I will present a different approach based on the sparsity. So let me start by some simple presentation of the problem. So the problem is quite classic here. We have already learned several times about this problem during these 2 days. We have capital T observations, which consist of a pair of input and output. The input is also often called the feature vector, which is x t here, and the output, or the label yt, will be assumed a real number. And it is well known in the learning theory is that if you take the quadratic laws, so if you try to predict the next value of y using a feature vector x t plus 1, and you measure the quality of your prediction, so b x t plus 1, here is the prediction of y t plus 1. If you measure the prediction here, the quality of the prediction here by the square laws, then the best possible predictor is the conditional expectation, which is defined here. So it's what usually known as bias predictor. And if you try to compute what is the conditional loss of this bias predictor, then you simply find the conditional variance. Okay, so S star squared here is the conditional variance of yt plus 1 when we know the feature vector x t plus 1. And the aim of this work will be to estimate the function b star and the function s star in a joint manner. So a little bit more statistical presentation of the problem is just to write it like signal plus noise. So we can write yt as the conditional expectation, which is b star here, plus the noise term, and the magnitude of the noise will be proportional to S star of x. And xit here is just will be assumed to be a vector of IID random variables. So in the theorem that I will present here, I will assume that they are Gaussian with zero mean and variance equal to 1, but you can extend it to slightly more general distributions. One thing is sure is that the conditional expectation of xi here, knowing x is equal to 0, and the conditional variance of xi knowing x is equal to 1. And so the aim is to estimate these functions b star and s at the same time, and to have a computationally tractable procedure with some theoretical guarantees, which will be in terms of the sparsity indices that I will introduce a little bit later. Okay, so the assumptions that I will impose here, so there will be some assumptions on B star and some assumptions on S star. So they will be sparsity assumptions. And basically they will mean that these functions B star and S star are not too complex. Okay, so they are living in a low dimensional space. Usually we don't exactly know where this low dimensional space is, but we know that there is some low dimensional space to which B star or S star are supposed to belong, or to be close to this space. And the classical example, which has been the focus of a lot of recent work, is a well-known homoscedastic regression model where all the noise levels are assumed to be equal. So the conditional variance here is constant and it doesn't depend on x. So it denoted sigma star. And then what one can do, one can decompose the unknown conditional expectation B star in some dictionary, which is called here F1, F2, Fp. So you have some functions, I mean a finite number of functions, usually you take an over-complex system of functions in order to get some good representation of your unknown conditional expectation. And the sparsity assumption says that basically P here, which is the real dimension of the problem, is very large, possibly much larger than the sample size capital T. But there are only a few of these functions F that contribute to computing this B star. So the coefficients beta star, which are here, contain only a very few non-zero elements. So it's written here. So if we denote by P star the L0 norm of this unknown vector beta star, which just counts the number of non-zero components in beta star, this P star, which I will sometimes call the intrinsic dimension of the problem, is much smaller than the ambient dimension, which is P. So just a few remarks concerning this problem. Even when the dimension of the original regressors xt, or original features xt, is equal to 1, the problem is not easy because we have to estimate two functions which are, I mean, in general any functions, and the problem is basically imposed because we have a finite number of observations and we want to estimate some infinite dimensional object. The literature on estimating a star is much scarcer than the one concerning the estimation of beta star. And, but I mean, estimating a star is almost as important as the estimation of B star, because if you predict something, you need to explain what is the uncertainty related to your predictor. Okay, so usually it's very useful to provide some confidence interval around your predicted value, and this is something which can be basically done if you have an estimator of a star. Yeah, final remark is that the case of inhomogeneous, of the time inhomogeneous observations is included in the previous framework in an obvious way, because we can always add the time in the regressors, in the feature vector, and then just doing this simple transformation of the feature vector, we can get a new conditional expectation and conditional variance which do not depend on it. Now let me explain the major part of the previous work on which we will rely for deriving our estimators. And for this, let me focus on the classical linear regression model. So as I have already presented on this slide, if we consider the homoscedastic regression, basically replacing B star by this expression, we reduce the problem to the problem of high-dimensional linear regression, which is written here. So X, the matrix X here is the design matrix, and if you look at the definition, it's exactly what has been written 2 slides before. Okay, so the entry xtj of this matrix X is just the j's element of the dictionary evaluated at the point X. And basically here we have a large dimensional vector beta star and a constant noise level sigma star. Then we need to estimate these two parameters by assuming that beta star is sparse, that is, it has only a few non-zero components. And the most popular approach is for solving this problem, or the lasso of Tibshirani and the Danzig selector of Candes and Tao. Basically what they do, so I will start by presenting lasso. It takes the negative log likelihood of the Gaussian distribution and penalizes it by an L1 type norm. Here you can remark that it's not exactly the L1 norm, but it's a kind of weighted L1 norm. And usually, if you have regressors which are not normed, or you don't have all the norms equal to 1, it's the right way of using the lasso penalty. And the nice feature of this penalty is that it is solving a second-order convex program, and it can be computed efficiently even for very large dimensions. Another proposal made by Candes and Tao in 2007 was to replace this original problem of penalized log likelihood estimation, penalized log likelihood minimization by constraint minimization, in which the constraint is basically a relaxation of the first order conditions of this optimization problem. So you just compute the gradient of this function with respect to the unknown beta, and you relax a little bit the condition that the gradient is equal to 0. Okay, so if you relax the condition in order to get a convex set, then you get this kind of inequalities. The nice feature here is that each inequality here can be written as two linear inequalities with respect to the unknown parameter beta. So basically the cost function which is minimized here can be replaced by a linear cost function, and all the constraints are also linear. So the Danzig selector can be computed solving a linear program, and once again it can be done very efficiently for very large dimensions. And so we see that these estimators are computationally tractable, very interesting for applications. And another advantage is that there is a very well developed theory for these estimators now. Basically the theory says that if we choose the tuning parameter lambda here proportional to 1 over sigma star, and if we assume that so lambda proportional to 1 sigma star is here, okay. And here it should be lambda proportional to sigma star. And if we assume that x is nice, then there are some sharp oracle inequalities, for instance those proved by Bickel and Ritov and Sibakov, and also there are sharp oracle inequalities in Canvas and Tau that prove that the prediction risk of the estimator, so beta star, beta dot here is either beta Danzig selector or beta lasso. So both of them satisfy oracle inequalities in which we see that the risk is upper bounded by a quantity which involves the intrinsic dimension divided by the sample size, and the ambient dimension is just inside the logarithm. Okay, so it depends only very slowly on the ambient dimension. But one thing that one can observe here is that in order to be able to correctly tune these two estimators, usually it is necessary to know the noise level sigma star. So after this observation, which says that the sigma star is, and it should be known, or at least approximately, in order to guarantee good theoretical performance for Danzig selector and lasso, several papers proposed to estimate the sigma star and the vector beta star in the same time. And the first one that I know was the paper by Stedler, Van de Geer, and Bulma in 2010, in which they say, okay, the idea in lasso was to minimize the log likelihood plus a penalty which is a weighted L1 norm. When sigma is unknown, we will do exactly the same, but the log likelihood of the Gaussian density will be different, okay? Because now sigma is unknown, so we have to include all the terms which depend on sigma, and the minimization should be carried out over all values of beta and all values of sigma. So this results in the very simple optimization problem which is written here. So you minimize with respect to all possible vectors beta and all possible positive values of sigma here. If you remove this term, it's just the definition of lasso. But when you add this term, you get a new estimator which is called scaled lasso. And another nice feature of this minimization problem is that it can be rewritten. If we do a very simple change of variables, we take 1 over sigma equal to rho and beta over sigma equal to phi. Then in terms of rho and phi, the cost function which is here is convex. Okay. So the original cost function here is not convex with respect to beta and sigma, but this transformed cost function is convex. And of course, the optimization problem which is written here and the one which is here are completely equivalent. Okay. So we can compute scaled lasso estimator by solving a convex optimization problem. Yeah.
So lambda here is known.
Lambda here is fixed. Lambda here is fixed. Okay. Actually, I will come back to this on the next slide.
In principle, you could also do cross validation or something.
Yeah. Okay. So very nice remark. The problem with cross validation is that you have to specify a grid of values for lambda over which you do your cross validation, right? I mean, it depends what kind of problem. There is no real consensus on this team for doing cross-validation for lasso. So either you use the fact that there is a path of solution which is piecewise constant, piecewise linear, and you do a cross-validation on that, but there is no theory for this estimator. Okay? Or you say, I fix a grid of values, and I do a cross-validation, I leave one out, cross-validation, something like that, over the grid value. But even if you do that, when you choose your grid, you should know where your sigma is, more or less. Okay? From this point of view, it seems more advantageous to use an estimator which estimates in joint manner phi, beta and sigma. And so a version of this estimator has been also proposed by myself and Yin Chen in 2012. And so when Sarah and Steller and Bulma propose this estimator, they have a theory, but their theoretical results, so they apply it in a more general setting of mixture estimation, and their result, since it covers this general case, it's not optimal in the particular case which is presented here. So in the particular case of multidimensional linear model, the results which are the sharpest at the moment have been obtained in our paper, and basically what they say, this result is that under the same assumptions as before, as for the lasso and the Danzig selector, we have exactly the same type of guarantees for the estimator which is here, with a choice of lambda which is completely independent on the noise level. Okay, so this is the main point here, is that the lambda doesn't depend on the noise level, it depends only on the sample size t and on the dimension p. Another estimator proposed in this framework is the one which has been termed square root lasso by Belloni and Chernozhukov. Basically, the first place where this estimator has been mentioned was a small discussion of Antoniadis to the paper of Steller, Vandenier, and Bulma, but the real theory for this estimator has been done in Belloni, Chernozhukov, and Wang, and also in a more recent paper of San and Zhang. The idea in this estimator is simply to make the cost function homogeneous with respect to beta. So in the original lasso, the problem that has been solved is the one in which we have a square here. So their proposal was just to remove the square in the data fidelity terms. And when we remove the square, it has been proved that one can obtain the same kind of guarantees as before for a lambda which is independent on sigma. And in the case of instrumental variable models, the similar idea has been used in Goitia and Sibakov 2011, and they have an estimator which is pretty much similar to the square root lasso, but which is written in a different form, which allows a very easy extension to this model of instrumental variables, and which provides very nice theoretical results as well. Okay, so I'm going to go a little bit faster. So now let me come back to our original problem and to explain how all these ideas can be extended to the case of heteroskedastic variance. So as you have seen before, so as shown on this slide here, when we use the penalized log likelihood, the nice trick was to make a change of variable in order to obtain a cost function which is convex. So we will use a similar kind of trick in the case where the variance is a function of the feature vectors. So what we will do, we will define two new functions. The first one, which is denoted R star here, is just the inverse of the conditional standard deviation, so it's just 1 over S star. And we will replace the regression function B star by its scaled version, which is just B star divided by S star. Okay, so it's kind of signal to noise ratio, which is here. And instead of estimating the pair of functions S star and B star, we will estimate the functions R star and F star. And if we rewrite the original problem, so I recall here that the original model that we have assumed is this one. So we replace B star and A star by their expressions which are here. So we divide basically the equations by A star of xt, and we get a new way of writing the problem, which is here. And the net property here is that this is something which is linear with respect to R star and F star, which was not the case previously.
Times xt or something. F star times xt.
No. Why?
What is the difference?
No, you have this.
This are already contained.
You have this. You divide by S star.
Ah.
So you put S star xt here. S star xt here. And here is cancelled now. Okay. And now this one is just F star, and 1 over S star is R star. So we have exactly this expression. And now we would like to estimate the pair of functions R star and F star. And of course, for estimating these functions, we will put some assumptions on them. And the assumptions are that the function F star, we will be able to decompose it in a dictionary. So just like in the linear multivariate linear regression model, we will assume that there is a dictionary of functions Fj. We will assume that F star can be written as a linear combination of these functions. And so we will consider a slightly extended version of sparsity, which is the group sparsity. We will assume that this vector phi star is group sparse with known groups, which form a partition of the set of all possible dictionary elements. And concerning the function R star, we will have a simpler assumption which simply says that our function is linear with respect to some functions of another dictionary. Okay, so we will have another dictionary of known functions R of L, and R star will be a linear combination of these functions. So here we will what we should retain is that P is very large, K is very small as compared to P, and Q is small. It's not equal to 1, but it's small. So, because of lack of time, I have to skip several slides. And if we replace in this equation that I have written here the expressions of F star and R star, then we just get some matrix vector products. So it's quite simple. And if we write all these vector of unknown values as the product of a matrix with an unknown vector, and we do the similar thing for R star, we get a kind of multi-dimensional linear regression model in which the matrix X star is the design matrix, R is the design matrix for the conditional variance, and dy is just a diagonal matrix on which diagonal elements are equal to y of t. And when we have this expression, it's just very clear now how we will estimate the vectors alpha star and phi star. We will just do the same trick as in Stadler, Van de Geer, and Bühlmann. We will penalize the log likelihood of this Gaussian model. So we have the Gaussian log likelihood, which is written here. It's just the logarithm of the variance plus this quadratic term, and we add this sparsity promoting penalty. We get a problem which is convex with respect to alpha and phi, and we can solve it by using some standard methods. So the slight problem here is that the cost function that we have, okay, it's convex, but it's not very easy to handle. So an alternative that we have proposed is just similar to the Danzig selector. We can write down the first order conditions to compute the convex relaxations of them, and to get another optimization problem which is quite close to the previous one, but which is just a second order Kohn program. So it can be solved by any solver performing second order Kohn programming. And how much time? Yeah. So just some comments on the procedure that I have shown. So one apparently unpleasant thing is that if you look at the penalty here, originally in the lasso there were one tuning parameter lambda. Here we have many tuning parameters lambda k. Okay, of course it's not a good thing to do, but in practice there is only one tuning parameter because a very simple theoretical analysis shows that all this lambda k should be equal to some constant lambda 0 multiplied by the square root of rk, where rk is just the rank of some part of our design matrix. Okay? So the design matrix is known, this rank can be computed, and the only tuning parameter that we have here is just this lambda 0. So there is only one tuning parameter, and another interesting thing is that we can add new constraints to this optimization problem, which says, for example, that our variance is bounded by some constant, or from below or from above. All these constraints will be just linear functions of alpha, so the program which was a second order comp program will remain a second order comp program. And also for more numerical results, there is a very well-known trick. Usually when you use lasso type estimators, you have a bias to 0. And to correct this bias to 0, people usually use a two-step procedure. At the first step, they use lasso to estimate the support, and then they do a classical least square estimator in order to estimate the vector just on the support. The same thing can be done here. We can use at the first step this algorithm, and then to restrict ourselves to the support, and then to perform a least square regression, which is equivalent to taking the same estimator as before, but with lambda equal to 0. And we have two implementations of this procedure which are available. We can send you it if you are interested in. One implementation is using the well-known interior point method, which is a second-order method of optimization, and there is another implementation using first-order proximal method proposed by Candace, Baker, and co-authors in the package tfrogs. So the theoretical result that we have is the following one. So if we assume that the errors are Gaussian, and if we choose these tuning parameters in the following way, so you can see that all the quantities which are involved here are known. Then we can estimate the prediction error for estimating this phi star. We will have the rate which was quite expected, and the same kind of inequality holds also for the estimator of alpha star. Okay. So just I have to precise here that I didn't divide all the terms by square root of t, but the right normalization here, I mean, I remove the division by square root of t in order to keep all this on one line. But the term here is traditionally proportional to square root of t. So in order to have the real prediction error, you should divide by 1 over square root of t, and then we get the error rate, which is square root of q divided by t, and the maximum between the square root of q divided by t and square root of p star divided by t, which is basically the best possible thing that we could expect in this situation. Just to summarize, so we have two new algorithms for estimating the conditional mean and the conditional variance, which take advantage of group sparsity and which do estimation by solving convex problems. And we have also did some numerical evaluation of the algorithm and comparing it with other state-of-the-art algorithms. Basically, in most situations, it's really much better than the existing results. So all related material is available on internet. Thank you very much.
Questions?
You could have used square root lasso also. Why did you use this version of estimator?
Yeah. Because I don't know how to, so there are two reasons. For the first reason, I don't like square root Lasso. Basically, this is the most important reason. I think, I mean, why I don't like square root Lasso, because for me, it's just some mathematical convenience. It's the origin for square root Lasso is just okay to say I will take the penalized log likelihood and I will make it homogeneous. Okay. There is no real statistical reason behind all that. So
Actually, there is.
it's my interpretation.
Actually, there is.
There is an optimization reason behind, but it's not.
No, there
We
is
can
a
discuss.
particular
So the dependence on the variance for square root Lasso is not good. It's sigma sub 1, it's not sigma in the bound. So
Actually, it depends on the condition.
Okay, but the other reason is that I cannot I don't know how to generalize square root Lasso to the case where the S is not constant.
So I missed something. The dictionary on which you expand S, is it the same as the one along which you expand
No.
the signal?
No.
And how do you get this dictionary?
So it's up to the user.
Okay.
So it's like yeah, you can take the wavelet dictionary.
like it's
So can do yeah. There's no real example where you would need anything other than some basis. Because when you do linear regression, you're given the x's, right? And you're given what you're given, and you're just hoping that this is
No, not always. Because for instance, when you are doing image analysis, you know just the pixels and what you use some wavelet basis, rotated wavelet basis, so you use some overcomplete dictionary of your functions. And this is not really given, it's the user chooses the dictionary. So the same can be done for the dictionary of power also.
Other questions?